So in this video, we're going to go through the OCR specification looking at electric and magnetic fields. So there's a link in the description of this video to the template that we're going to be working through, which you can see on the right hand side. So do find that and download it so you can work through it. So what you need to do is, with this booklet, what I'd like you to do is attempt to work through each of the sections that is in it, and then what we're going to do is we're going to review that section in terms of the knowledge that you should have, but it's most effective if you work through it first of all, put what you think should be down there, and then we'll edit it as you go through. And again, the reason I've given a digital copy of the booklet is not just so you can work through it, but this is a task you should be able to do again and again and again to see how your knowledge develops over time. Another resource I put together to help you with this is a Memrise course looking at the different definitions. So I've put again a link in the description to the fields course that I've created so that you can get to the point where these definitions come easily without effort to remember them. Okay, so let's get started looking at capacitors, which is section 6.1.1. So we're going to look at what capacitance is and what happens when you have one in a circuit. So what I'm going to do is pause the video now and work through the section on capacitors. And then what we'll do is review what you've got. All right, so I'm going to assume that you've worked through this section now. So let's take a look at capacitance. So capacitance is the amount of charge that can be stored per unit volt of potential difference across the capacitor, and capacitance is measured in the unit of farads, named after Michael Faraday, who did a lot of work with electric and magnetic fields. So the equation essentially comes from that definition because it's the charge per unit volt there. So thinking about what's happening when a capacitor charges and discharges in terms of force and flow of electrons. Thinking about charging first of all, so the reason anything happens at all is because the EMF source you put in provides a force from its electric field. That's what's causing movement to happen. So initially, that's the only force in your circuit. So when you apply the EMF source, there is a force to make electrons move around the circuit. However, what happens is, as electrons build up on the capacitor, a force is induced that opposes the EMF source, and that force gets bigger and bigger and bigger the more charge there is in the capacitor. And what that does is it decreases the rate at which charge can flow around your circuit. So that's during charging. During discharge, there is initially a large electrostatic force to push electrons off the capacitor, and that force comes from the other electrons that you've stored on the capacitor. And what happens is, as the number of electrons on the plates reduces, the force is going to decrease, and therefore the rate at which the electrons flow around your circuit decreases. So during both charging and discharging, we get a decreasing current over time. Okay, so what we're going to look at now is combining capacitors together in a circuit. So first of all, in series. So if they're in series, what happens is the potential difference gets divided between the two capacitors. We know that from Kirchhoff's second law, and that has the effect of decreasing the overall capacitance in the circuit. Whereas if you have them in parallel, they have the same potential difference, so you can store more charges, so you can have a larger capacitance. Okay, so that's the fundamentals of capacitors. We'll now take a look at them in terms of their energy. All right, so let's first look at energy stored from a graph. So the graph that we need is the Q versus V graph. So with previous circuitry, you would have probably used the equation work done is equal to QV, or the number of charges times the potential difference, which is great if the potential difference is constant, but what you're actually doing there is finding the area under a Q versus V graph, but V happens to be a constant. So in this situation, V is not constant, so the area is actually calculated using half QV. So that's how we calculate the work done on a capacitor and therefore the energy stored in the capacitor. So that's one way of doing it, but we can make substitutions into that equation to find others. So if we make Q equal CV, we can put that in, or if we make V equal Q over C, we end up with the equation on the far right-hand side. All right, so in terms of identifying what we use capacitors for, we use them for any application that which we need a very high rate of energy transfer or high power. So when we want to store energy very quickly or we want to discharge energy very quickly, they are far better at that than batteries are, which get damaged by very rapid charge and discharge. So one of the systems that use capacitors would be an ERS system or an energy recovery system. They use quite commonly F1 cars, but things like normal cars have started using them as well. And the other thing that's quite commonly used for that you might have come across is the Emirates airline in London. Each cable car has its own battery, and so it powers itself across the line, and it gets charged as it goes through the docking station. So that's another use for it. There are lots more, but those are just some examples. Okay, so moving on to modeling charging and discharging capacitors in terms of their performance. So these are the things the specification says you need to know or be able to do. So let's take a look. So again, pause the video, work your way through this section, and then we can review it a bit later. All right, so now you've worked your way through, let's have a look. So initially, potential difference across the resistor is equal to the EMF of the power source, because the capacitor has not yet got any potential difference when you start charging it. So that's going to give you the largest possible current because there's no potential difference opposing the EMF source. So that's why we start off with high current. And as you store charge on the capacitor, its potential increases, and therefore the potential difference across any circuit resistance is decreased. And therefore your current decreases as well. And eventually the potential difference across the capacitor is equal to the potential difference across your EMF source. So then the potential difference across the resistance would be 0, so your current is then 0. Now we can do the same process when we're discharging. So initially, potential difference across the resistor is equal to potential difference across the capacitor because we've taken away our EMF source. And then as it discharges, the potential difference across the capacitor decreases, so therefore so does the current. And eventually the potential difference is 0 across the capacitor and the current becomes 0, but we never really usually get to that point. Okay, so we can actually get better models for it than just describing what happens like we did there. So we can actually get discharge graphs for different resistors so we can understand their performance. So we're going to talk about the way you would go about producing those charging or discharging curves. So if we're doing a charging curve, we'd want a circuit like this. So we need a voltmeter, so we know what the potential difference is, and an ammeter, so we can know what the current is, and from that we could work out the charge. And if we want to do a discharge curve, it's the same circuit, but there's no power source. We'd have need to charge up our capacitors already. So what we're going to do is we're going to connect the ammeter and the voltmeter to a data logger because we're going to want to take readings continuously over a period of time. That's what we use a data logger for, and most devices have the ability to, most digital measuring devices have the ability to be connected to a data logger. So we can plot their values over time. And so we can straight away get graphs of potential difference and current versus time. So the thing is, how do we get the third graph, the one of charge versus time? Well, from our current graph, we can work out what the current equation is. And by integrating that, we can work out the amount of charge we've stored or the amount of charge we've discharged from our capacitor and plot that as a graph as well. So there's no direct way of measuring charge in a circuit, but we can quite easily find out what it is from the current graph. Okay, so the thing we use to describe how effectively a capacitor can charge or discharge, or the rate at which it does those things, is the time constant. And we can define it in two ways: the time taken for a discharging capacitor to reach 37% of its initial PD or charge, or we can define it as the time taken to reach 63% of the final PD or charge when you're charging it. So either of those works, and what it turns out is that value of time constant is equal to the resistance times the capacitance in your circuit. Okay, so we end up with graphs of the charge, the potential difference in current, but what would be nice is if we can come up with equations that model the same thing, and we can. So for a discharging capacitor, we end up with these equations here. So the potential difference, charge or current at any moment in time depends on the initial values of those and the time constant like this. And for a charging one, it looks very similar, but slightly modified, but those are the charging ones. So the reason we know it's an exponential type relationship is what we find is the rate at which a capacitor charges or discharges depends on the number of charges already on that capacitor. That's the characteristic of an exponential relationship, is where the rate of change of something depends on the amount of that thing. That's what gives it exponential. But we can show where this relationship comes from. So first of all, you should know that dq dt is going to be equal to the current in the circuit. And it's actually going to be minus the current because it's discharging going in the opposite direction. And we should know if we use Ohm's law, we can substitute in V over R for that value. And using Q equals CV, we can substitute that in for V, and we end up with dq dt is equal to minus Q over RC. Okay, so like I said, these characteristics describe an exponential graph. So how do you recognize an exponential decay graph? Well, what you should find is the change in x for the property on the y-axis to halve must be constant. So for a capacitor, what that means is, because time is always on the x-axis, the time taken for the charge or the potential difference to halve is constant. So the time to go from fully charged to half charged is the same time as it takes to go from half charged to quarter charged. That's what an exponential relationship looks like. Okay, so we're now going to move on to studying electric fields in more detail, because that's what we effectively create with a capacitor. We create an electric field on the capacitor. So let's describe first what we mean by an electric field. It's essentially the region around a charged particle where another charge will experience a force. A field, generally speaking, is a region where an object will experience a force. An electric field is where a charge will experience a force. So a very common device you come across, a Van de Graaff generator, it has a sphere on the top and the charge gets spread out over the sphere. But just like with gravitational fields, we don't really deal with fields as three-dimensional objects at all. So what we do is we model the sphere as a point charge at the center of the sphere. So we essentially take all the charge and say it's concentrated into a single point, just like we do with gravitational fields, where we take all the mass and say it's concentrated to one point as well. So we do the same approach with electric fields. So the fields look slightly different around positive and negative point charges. So a positive, the field lines will be going away from it. So field lines always go from high potential to low. So remember, infinity is always zero potential. A positive charge has positive potential close to it, so they're going away. Whereas negative charge, they're coming towards it because it goes from zero and it becomes negative. So they're always going from high potential to low potential. And we can use these field lines, or the density of these field lines, to define electric field strength. So electric field strength is the force experienced by a unit point positive charge. So unit means 1 coulomb, point means 0 volume, and positive, well, means positive or plus 1 test charge. And so it's very similar to gravitational field strength, which is force per unit kilogram. This is force per unit charge. Okay, so starting to look at some laws we use to model electric fields, and you'll see why we decide to model things as a point now. So Coulomb's law of charge is how we can calculate the force between charges. And what it says is the force between 2 point charges in a vacuum is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So when we model that sphere as a point charge, that then allows us to use this law for it. And it's often expressed as this equation, where we've got the two charges, the product of them on the top line, and the distance between them squared on the bottom line. And we have some constants, 4 pi, and the permittivity of free space, E0. So then if we know the force, and we know the field strength is the force per unit charge, we can calculate the field strength around the charge Q1. Okay, so I've talked a lot about gravitational fields alongside the electric fields to kind of show you how they're very similar. And so what we're going to do now is compare and contrast them, which means identify similarities and identify differences. So the thing you should have noticed for both is that the force or the field strength is inversely proportional to the distance squared. So they're the same, they're both points creating the field, and the exchange particles are all going out in all directions over the surface area of a sphere, so they both have this inverse square relationship. And we also get the same thing with potential or potential energy, that they're inversely proportional to distance as well. So those are the same. So where we start to get some differences is the electric fields can be either attractive or repulsive, and the potential energy can be either negative or positive, whereas gravitational fields are always attractive and the potential energy is always negative. So that's how one of the ways they're different. For electric fields, the force is proportional to the product charges. Gravitational fields, it's for the product of the masses. And a few final points is, so an electric field is infinite range, so every charge is in the field of every other charge. The force is mediated by virtual photons that travel at the speed of light, but these virtual photons can be blocked by the field of other charges. So those of you who do chemistry will know outer shell electrons are shielded from the nucleus by inner shell electrons, so you should be familiar with this blocking already. Whereas with gravitational fields, they're also infinite range. They have a different exchange particle, the graviton, which also travels at the speed of light, but the graviton cannot be blocked by the field of other masses, because gravity is a fundamentally different force to electric fields, so it behaves differently. Okay, so let's talk about how the field around charges leads to a force between them. So when we get two fields interacting, and as I said, all electric fields are interacting, those two fields superpose on each other. And if those two fields are the same type, so they're both from negative charges, that creates a force that pushes the charges apart. Whereas if the two fields are opposite, so one's positive, one's negative, when they superpose, that creates a force to pull the charges together. But this is why the two objects experience equal and opposite forces, because you need two fields to interact to get a force. That's how all forces are induced. You need two fields interacting. Okay, so starting to model a slightly different type of field. So we've been looking at radial electric fields. So now we're going to look at uniform electric fields, which are very similar to uniform gravitational fields. So the field strength in a uniform field is the same everywhere, and we can calculate it if we know the potential difference between the two plates creating the uniform electric field and the distance between those two plates. So it's very simple to calculate. And what we're going to start to look at now is, we already had a look at capacitance with a vacuum in between them, or we weren't aware at the time that that's what we were doing. But if we put another material between the plates, that's called a dielectric, we can affect the capacitance. So we can actually calculate the capacitance a material has if we know two properties. So if we know the surface area of the plates, that affects the capacitance. If we know the plate separation, that changes the capacitance too. And if we change the material between the two plates, that can change the capacitance, because it changes the the term you can see here called the relative permittivity, which is shown with an epsilon subscript r. So different materials have different relative permittivities. They're all greater than 1, so you can never have a permittivity less than E0, but you can increase that epsilon or the permittivity value. Okay, so now what we're going to do is we've talked about a uniform electric field. So now what we're going to do is we're going to describe what happens if we send an electron through a uniform electric field. And first of all, we're going to look at an electron traveling in the same direction as the field lines. So here's our uniform electric field, and field lines go from positive to negative. So we can put in the positive where the positive plate is. So our electron said is in the same direction as the field line, so our electron is traveling that way. But the electron is going to be attracted to the positive plate and repelled by the negative plate. So what's going to happen is the electron will experience a constant force, because it's a uniform electric field, in the opposite direction to its motion. So what it will do is it will slow to a stop, and then it'll turn around and increase its speed towards the positive plate and eventually collide with that plate. Whereas if we're traveling perpendicular, that means we're going across this way. We could be going across the other way. So the velocity of the electron parallel to the plate will be unchanged. So its velocity in the direction you can see there is going to be constant. But what's going to happen is it's going to accelerate upwards as well, which will create a parabolic type path, the same type of path as if you fire a projectile horizontally in a uniform gravitational field. But that one would curve downwards, this one curves upwards. So now we're going to think about electric fields in terms of energy as well as the force we've looked at. So electric potential is very similar to gravitational potential. So electric potential is the work done on a unit positive point charge to move it from infinity to a point in an electric field. And we can calculate the potential, which is given the symbol V, using this equation here. Okay, so now we've sort of learned some more about electric fields, we can go back to looking at capacitance, and we can do it for looking at the sphere that initially we modeled as a point charge. Because we're essentially using the sphere as a store of charges, like we're using it like a plate to store charges, so it's essentially a capacitance. So one of the relationships that you come across quite a lot with fields is that the relationship between field strength and the potential. So field strength is the potential gradient, which means if you integrate field strength between two distances, you get the change in potential between those 2 points. So if we're going to work out capacitance, we need potential difference for our sphere. So that's why I'm going through that step. So our sphere has a radius r, I've just called it capital R, and what I can do is I can integrate the field strength between 0 and r, and we end up with that expression there. And then plugging that into our capacitance equation, we end up with an expression for the capacitance of a sphere. So it's not just parallel plates that have capacitance. A sphere with charge built up on it also has capacitance. So let's look at a little bit more detail in the relationship we've just seen. So we've just seen that electric field strength is the gradient of an electric potential versus distance graph, or the derivative with respect to distance. But what we've just used is that the change in potential is the area under a field strength versus distance graph, which is the same as integrating field strength with respect to distance. And this kind of relationship applies to gravitational fields too. We get the same relationship between potential and field strength. And just like gravitational, we can calculate electric potential energy at a point if we know the two charges and the distance between them. Alrighty, so now we're going to move on to magnetic fields. So we're going to look at some basics to start off with and have a look at the fields around in different scenarios. And then we're going to move on to look at forces between two objects. So first off, let's describe how magnetic fields are created. So an electric field is created around a stationary charge. A magnetic field is created around a moving charge. That can take two forms. The charges can either have linear or straight line velocity, which is what's happening in an electromagnet, So we've got a current, which is moving charges, but we can also have charges with angular velocity, which means they're spinning, and that's what's going on inside permanent magnets or ferromagnetic materials. The charges have angular velocity, and that creates the field. So you should already be familiar with the field around a bar magnet. The field lines have a pattern like this, and the field lines go from north to south, so that shouldn't be anything new to you. But we can have a look at some more fields around different scenarios. So if we have a wire, we use the right-hand corkscrew rule, as it's often known, as a way of finding the direction of the field. So your thumb points in the direction of conventional current. Your fingers tell you the direction of the field lines in circles around the wire. So that's for a current carrying wire. If we have a coil, we get a slightly different effect. So you can see the current going clockwise around that coil. And we end up in the middle of the coil getting a fairly uniform magnetic field going through the middle, but we get those circles around the wire as you get close to the wire, as you might expect. And then the final one, a solenoid, which is essentially lots of flat coils lined up with each other. So what you end up with is this nice uniform magnetic field inside the solenoid, but then you get these loops of field around it as well. And that means the solenoid ends up having poles there, because we can see that the field lines are wrapping back around from the North Pole to the South Pole there. Okay, so what we're going to do now is use the idea of magnetic fields to explain how an electric motor works. We're going to use Fleming's left-hand motor rule to do this. So first of all, let's identify the field direction. So we can see field lines go from north to south. So we can see the field is going from left to right, or my first finger is pointing from left to right. And that will be the same for both sides of the motor, so that's not going to change. So if we look at the left-hand side of the motor, the side closest to the North Pole, the current is coming towards us, or in this direction, kind of out of the screen. So my middle finger is now pointing towards me. My left finger is pointing from left to right, which means your thumb is pointing upwards, which means that side is going to experience a force upwards. We're going to have exactly the opposite thing on the right-hand side. The current is going upwards on the page. Field is still going to the right, so force is downwards on that side. So then we've got here is two forces of equal magnitude making the object rotate in the same direction. So we've got a couple producing a torque, and it's going to produce that torque about the central axis on which it's rotating. And if we didn't do anything, that force direction would change every half cycle. So what we have is that device you can see on there called a split ring commutator, which is a fancy way of saying two brushes. So that allows us to change the current direction every half cycle, so the torque keeps going the same way, and we can use our electric motor to spin wheels or drive something that we're interested in. Okay, so what we can do is think about the factors that will affect the size of that force and therefore the torque. So we have this equation here. So we're using the force is going to be the magnetic flux density times by current times the length of the conductor inside the magnetic field times the angle between the field and the conductor. And we can use this as a way of finding out the magnetic field strength or the magnetic flux density of a field. So what we need to do is get ourselves a few components. We need an EMF source and a wire, a potentiometer. We're going to need an ammeter to measure current, and we're going to use a mass balance as a way of measuring force. And we're going to need the uniform field we want to investigate. So what we do is I'm going to identify things I'm going to keep constant. So I'm going to keep the wire perpendicular to the field the whole time so that theta stays constant. And I'm going to keep the length of wire inside the field constant the whole time as well, and measure actually what it is so I can use that later. Then what I do is I put the magnetic field on a balance and I zero it. So it reads 0 when the current is switched off. And then what I'm going to do is I'm going to turn on the circuit, and I'm going to use the potentiometer to change the current in the circuit. And I'm going to use the mass balance as a way of measuring the force in the setup. So what I'm going to do is I'm going to plot a graph of current against mass, find the gradient, and the flux density is going to be G, so 9.81 divided by the length inside the field, which I measured earlier, times the gradient. And the reason for that is the force is going to be the mass reading times by G. That's essentially what our balance is actually measuring force, and then it divides it by G. So we multiply the mass by G, gives us the weight force. So then we know it's perpendicular, so sine theta equals 1. And we've got current on the y-axis, so let's move all the terms to the other side, so we leave current by itself. And we can see that mass is multiplied by G over L times B. So therefore, that's why we use the gradient in the way we do. Okay, so that's how we can measure field strength using this equation. So that's actually used in the way we define magnetic flux density. It's the force per unit length per unit current acting on a wire perpendicular to the magnetic field line. So unit length means 1 meter, unit current means 1 coulomb, and the wire being perpendicular makes sine theta equal to 1. And we measure magnetic flux density in the unit Tesla, named after Nikola Tesla, one of the famous researchers about magnetic fields and lots of other stuff too. So now what we're going to do is look at the motion of charged particles in a magnetic field, because as I said, magnetic fields are created by moving charges, and that means that moving charges will also be affected by magnetic fields because they'll have their own magnetic field. So calculate the force on a charged particle at right angles to a field. So that's what this equation is for. We could also add a sine theta term in there if it's not traveling perpendicular to the field. And we can use magnetic fields to cause charged particles to move in circular motion, which was very important when we were trying to determine the characteristics of an electron. That was one of the ways we could control electrons. So one of the useful things about magnetic fields is the force is always perpendicular to the velocity, which is one of the conditions we need for circular motion. So as long as we can keep the magnetic flux density constant, we can create the conditions of uniform circular motion and essentially control the path of our electron into a circle, and then we can start taking measurements from it. Okay, so what we're going to do is explain how we can use both electric and magnetic fields to select charged particles of known velocity. So what I've got here is I've set up a uniform electric field with a positive plate on top and the less positive plate on the bottom, and I put a magnetic field going down into the page. That's what those X's show, a magnetic field going down into the plane of the page. So the force if we send a charged particle through parallel to the plates, the force from the magnetic field would be BQV. The force from the uniform electric field would be E times Q, which is VQ over D. So if we can have a specific scenario where those two forces are equal to each other, that will mean that the electron is traveling at a certain speed. So the electrons we want to come out of the other side of the plate are the ones where the force will balance. So we can choose the potential difference of our electric field to decide the velocity that will go straight through or experience no resultant force from the field there. So that's what it means so this is called a velocity selector. Okay, so that's how we will select velocities. We'll choose our electric field strength or a potential difference to give us the right velocity. Okay, so what we're going to do now is finish off by looking at electromagnetism, or how we can use magnets as a way of generating electricity, essentially. So these are the things the specification says we need to be able to do for this topic. So let's take a look. So we've defined magnetic flux density earlier. So what we're going to do now is define magnetic flux. So magnetic flux is calculated by doing magnetic flux density multiplied by the area of your conductor perpendicular to the field. So that's our definition for flux in terms of flux density and area. Flux linkage is when we don't just have one coil, for example, we have multiple coils. So flux is just for one conductor, flux linkage is for n conductors. That's where the n comes from. And the sine theta is in there to calculate the area perpendicular to the field. So theta is the angle between the field lines and the area that you're interested in. So then, in terms of induction, we have two laws that essentially govern it. We have Faraday's law, which tells us the induced EMF is directly proportional to the rate of change of flux linkage. And we have Lenz's law that tells us about the direction of the induced EMF, and that it's induced in the opposite direction to the change that caused it to be induced. So it essentially opposes the thing that's creating it. So from Faraday's law, we can essentially work out the EMF we would induce. So it's, as I said, it's the rate of change of flux linkage. Flux linkage was BAN sine theta. So if we take the derivative with respect to time, we end up with BAN cosine theta graph there. And it's minus because it's the minus sign from the minus dq, d flux linkage over dt. So we can actually investigate the amount of magnetic flux using something called a search coil. So we've got a big loop that you can see there, that's our field coil, so the object creating the magnetic field. And we've got a search coil that's essentially the area we're using to detect the magnetic flux. So what we're going to do is we're going to change the angle between the search coil and the field coil. So if we supply an AC supply to the field coil, what will happen is that will produce an alternating magnetic field. And as we saw earlier, if we have a current going around a coil, we get a fairly uniform field in the middle, but because it's AC, those field lines are going to be swapping directions all the time. So if the search coil, and usually it'll be a set of large number of turns, maybe 200, maybe 1000, is connected to an oscilloscope, if the two circles are parallel to each other, or theta essentially equals 0, what that means is we end up with a maximum EMF being induced because all of the area of the search coil is perpendicular to the field from the field coil. So we get maximum EMF. The reason we get a rate of change of flux linkage is because it's an AC supply, so that's giving us changing electric field. So when we just hold an area perpendicular to it, we get maximum EMF. Whereas if we make theta 90, so the search coil is essentially flat or parallel to the field, we're going to get the area perpendicular to the field is going to be 0, so the flux is going to be 0. But that's how a search coil is useful. It allows us to determine the flux, essentially. So power stations, obviously we want to be able to generate electricity, which means we're inducing an EMF. So it's a very similar setup to an electric motor, but with a couple of differences. So when the coil is in the position shown, it's cutting through the field lines at maximum rate. So the field lines, I imagine them going from north to south. So as the two sides of the coil are moving upward and downward respectively, those are going to cut through a lot of field lines, and you're going to get maximum EMF induced at that point. When the coil has rotated 90 degrees, the conductors are then moving parallel to field lines at that moment in time, so no EMF is induced. Okay, so the final thing we're going to take a look at is how a transformer works and explain how it sets up or down the EMF. So, and first of all, to make a transformer work, we need an AC current. It doesn't work if the current is not AC. So that's the first thing we need. And we send it through one coil, which is wrapped around the core. And we call that the primary coil because that's where we put the current in. And because it's an AC current, you get an alternating magnetic field around that coil. So the reason we have the core there is it's there as a magnetic field conductor. So iron, which is usually used, is a very good magnetic field conductor, and it conducts it around to the secondary coil. So because the secondary coil is stationary, but because the magnetic field is alternating, we've got changing flux linkage. So according to Faraday's law, an EMF is going to be induced in the secondary coil. So if the secondary coil has more turns and the flux is the same on both sides, there's going to be a greater rate of change of flux linkage on the secondary side. And that means a greater EMF is induced than the EMF that was used to create. So that would be an example of a step-up transformer. You have more turns on the secondary side, the rate of change of flux linkage is greater on the secondary side, therefore a bigger EMF is induced than was on the original side. The trade-off being you have to decrease the current to make sure power is the same on both sides. A step-down transformer is the opposite, so it has fewer turns on the right-hand side or secondary side, so then it has a smaller rate of change of flux linkage and therefore a smaller EMF is induced. So we've got some equations to model this. So it turns out that the ratio between the potentials or the EMFs on the sides is the same as the ratio of the turns. So if you have twice as many turns, you have double the rate of change of flux linkage, therefore you end up with double the EMF or voltage on that side. But as I said, the opposite thing happens with current. So if you step up the voltage, you step down the current to make sure power is the same going in as it is coming out. So that's in the opposite ratio there. And that concludes this video on electric and magnetic fields.